Hello, welcome back to S.T.E.M Online Academy. Today we're going to be talking about a very interesting topic. We're going to derive the escape velocity using calculus. Again, I repeat, we're going to derive escape velocity using only calculus. Okay, so today's going to be a physics day, right? Because that's what S.T.E.M Online is. We specialize both in calculus and physics-based courses. All right, so let's get right to it. Okay, so I'm going to use calculus to derive this. And I'm going to do that because I think a lot of you in high school, obviously high school, but in university too, unless your professor showed you how to derive this formula. I'm going to emphasize here, right? The escape velocity equals the square root of 2gm over r. Okay, so let's get to it. Right, so what we're going to do is we're going to draw a diagram. Okay, let's draw a diagram here. Okay, so we've got, so for this proof, okay, so the proof, remember my four-step method, my systems technique to solving math and physics problems. Okay, it's visualize, model, right, execute and verify. Okay, actually I should write that first. My systems technique. Okay, systems technique for solving problems. That's really large, sorry. Technique for solving problems, okay? So, systems technique. All right, so when it comes to the systems technique, right, step one, we're going to visualize the problem, okay? Visualize. Model. Execute. Verify. Right? So when it comes to this technique, the first thing we are going to do, okay, is we need to visualize the phenomenon, okay? Now, the question is, we want to be able to first, uh, you know, see how the rocket or object will leave Earth's gravity. That's what's asking, right? To get the escape velocity, we want, in reality, we want, we want to figure out its velocity, what velocity is needed to escape Earth's gravity. And that's what we're trying to prove here. Okay, so let's do that. So, but before I do that, before I do the proof, I am going to talk about something very important. Okay, I think that a lot of you will be able to identify. Okay, at one point, I sucked at basic math. Okay, this is the truth. I don't sugarcoat things. I say what it is, even if it's a negative for me. At one point, I really sucked at math. Okay, from grade 7 to grade 9ish. Okay, it wasn't that like I was stupid or anything. It was the fact that I didn't know that you need a system for solving mathematical problems. There was a hard differentiation. I'm sure a lot of you can sort of identify with this. Is that a lot of math can be rote, okay, rote and easy, and too many schools, junior high schools and high schools, are giving you problems that are very algorithmic. Okay, it can make you think you're understanding math, but you actually don't. Okay, And the problem with that is, and that's why a lot of people have problems with tests, because they're able to do very well on these routine based problems, but when it comes to tests or exams or whatever, they screw up. Especially final exams, they have a lot of trouble. It's like, wait, I know everything. I think I understand. No, you may know it, but the system hasn't taught you to really know it. Okay, I was lucky to have two teachers that changed that for me. All right, two, one at the end of junior high school, one in grade 9. That where my improvements started to um, really skyrocket. Okay, they told me that I need a system. Right, I needed a system that involves also not being anxious, because a lot of people are anxious when it comes to math and physics. They get really scared, they're actually terrified, right? But if you go into a problem being emotional and first off, if you're emotional, you won't have a plan. You won't have a plan that works. Okay. Every plan I've had that was emotional just went to crap. It didn't give me anything. That's from my personal experience. So first off, you want to make sure that you calm down, deep breathe when it comes to any type of problem. Okay. And then you want to apply a system. Okay. And that system, right? Doesn't have to be my system, it can be any system, has to be a step-by-step logical progression. Okay. Now, when it comes to physics, it's slightly different. It works for math too. It's the same. For physics, a bit more. For me, it was the visualize, right? The visualize part, then model, then execute, and verify. Okay. And this system that I'm showing you is going to be way better than any AI or artificial intelligence system can show you. Because artificial intelligence can give you the answer, it can show you the some of the steps, or a lot of the steps. But when it comes to those tests and exams, it is you who is responsible for it. There's not going to be any AI to save you. There's not going to be any AI to give you the intuition to solve a hard problem. Right? You have to have that system. Okay. And this system here really saved my life. Saved me in high school. I did very well at the end. And in university, I skyrocketed. 3.85. Yeah, it was 3.85 GPA. 3.9 or something out of 4. 3.85. It's more accurate. I used to be saying 3.85. Yeah, 3.85 GPA in mathematics and physics double honors. Okay. So, as I said, let's use this technique. Okay. And I'm going to show you why it's so effective. All right. So, for this proof, okay, because we have to derive, derivation is not the same as proof, but I'm going to say proof anyways. Proof. Let's draw both a physical representation and a geometric representation. Okay. The physical representation, okay, the physical representation will be this. Okay, so we have Earth. Okay, I have Earth here. Just give me a sec. I'm going to call it capital E. Earth. And we also have, let's say, some orbit. Let's create an orbit. Okay, so let's do that. Right, let's call this portion here little a. Okay, call R1, doesn't matter. R1 will represent um, from the center of Earth to the surface, the radius of Earth. Let's call it our Earth. So Earth. And then from the center of Earth's core all the way to the axial orbit, Once we reach the orbit, that will be, we've escaped Earth's gravity. I'm going to call this our satellite. Okay, so now we have this. All right. So how are we going to do this? So here's a physical representation of the visualized part. So step one, visualizing. One, we visualize. Right, so we visualize. Okay, so we're visualizing. So we have that. Now, since we're going through the visualization part, right? That's the physical representation. We also have a geometric representation. Let me explain. Actually, before I do that, I'm going to go right into what's law we need to use, okay, to do this. We're going to use Newton's universal law of gravitation. Okay, so that is Fg equals G m1, m1 being m Earth, let's say me. Okay, so m Earth, satellite, divided by the distance between the spherical objects, r squared. So a, right? A squared. Okay, this is Newton's law of universal gravitation. Why am I using this? There's a reason why I'm using it. So this is by Newton's universal law, law of gravitation. All right, so the reason for this is because we want to escape Earth's gravity, right? So we have to get off of planet Earth. The thing is, the rocket, let's say you have a rocket, the rocket is on the surface of Earth, okay? So that means that it's at a distance r Earth. Right, so r Earth. So it's somewhere over here. Okay, so let me just say this, let's say our rocket or satellite is over here on the surface, okay? Now, in order for it to escape Earth's gravity, we're going to get out of this orbit. So to do that, right, to escape Earth's gravity, okay, as we're escaping Earth's gravity, the distance from Earth's surface goes from the Earth's surface all the way out to wherever that orbit is, right? But the further away that satellite goes from Earth, in Earth's center actually, its gravitational attraction starts to decrease. Okay, see here, as r increases, right? As r increases, Fg would decrease. So we also have to make a physical model, a geometric model. Sorry, I'm going to explain that. So here's a geometric model. Okay, so a geometric model is like this. Squared. And we have curves like this. Okay, so the curve is going to look like this. This is our geometric or graphical representation of what's happening to the gravitational attraction as the satellite leaves Earth, and tries to escape Earth's gravity. Okay, how do I know it's like this? Because mathematically, okay, if you look at Newton's universal law of gravitation, G, M, and M Earth and M satellite are constants, right? G is a gravitational constant, M is a constant. The masses are constants, right? Um, only R is changing. R is independent of everything. So in reality, I can put a proportionality constant, if that makes sense. You've heard of proportionality constants before, right? In reality, we can say that Fg as a function of A, because this is a function of R is independent, so it's like our X is a function of X or a function of A, is equal to K. K is a proportionality constant divided by R squared. Okay, so this is what we have. And if you can relate this, this is very relevant to 1 over x, 1 over x, the graph for 1 over x squared. 1 over x, yeah, something like that. Okay, so this is what we've got. Actually, 1 over x squared. Something like this. 1 second. Made a slight mistake. This curves up there. Okay, but you can see we just need one branch. This one branch tells us enough. It tells us as r increases, fg is decreasing, right? Very simple. Now, since we know that, let's look at fg. What I'm going to do is I can also rewrite this using some calculus notation. Okay, so let's do that. Let's use the limit, right? The limit as a approaches infinity of capital Fg, so gravity is a function of r, right? Right, we can say this is equal to limit as r approaches infinity, g being, let's see here, this is going to be k over g m earth m satellite all over r squared. Okay, as r goes to infinity, fg is approaching 0, right? That should be the logic here. Yes, as fg as fg g as sorry, as r approaches infinity, fg approaches 0. As r approaches infinity, then fg approaches 0. Okay, so this is what we have. Now, with that, right, as r is getting very big, fg is approaching 0. Sorry, what am I doing? My apologies. Mistakes happen. Right. But I think in the comments, if you want, if you have any questions or if you'd like me to elaborate more, or if you uh, need coaching on this, I'm always available. Uh, my website will be in the link below. So this is what we got. Now, what we need to do is we're going to be looking at, okay, taking R2 and approach infinity. Our Earth, this is where our Earth is. Let me see here. So we have to figure out which R we're talking about. So you have to be very careful. Which R, okay, so which R are we talking about when I mean R approaches infinity? Our Earth or our satellite? That's a very good question. It's the R satellite. Okay. because we're trying to get that satellite out to infinity. So our satellite is approaching infinity. Okay, so our satellite distance from the center of Earth to the orbit outside of Earth's gravity. That's what our satellite is. Okay, so this guy right here. All right, so we got that. Now, our satellite. So this is all our satellites. Our satellite, our satellite, our satellite. We have our satellite. Okay. Now from here, what we're going to do is we're going to start modeling what we need to do. Right? I gave a very deep, in-depth visualization, both a physical representation above, right, with the Earth and the satellite, that's physical, then a geometrical graphical representation of the behavior of what's happening. Okay, so now we have all this. Okay, we have all this information. Step two is to look at the following. Okay, so step two is to finally step two is to do the following. Okay, so step two, we're going to do this. Okay, we're going to model. We're going to model the framework of how to solve the problem. Okay. Okay, so step two is to model. Okay, so what I mean by model is I mean to come up with a framework for the physical reasoning or physical intuition to the physics problem. Okay, so we know that the following. Okay, we know the following. We know that as our satellite approaches infinity, then FG approaches zero. Okay, that's one of the physical representations of what's happening. So as our satellite approaches infinity, FG is approaching zero. Okay. Another thing is, as FG is approaching zero, its gravitational potential energy has to be increasing because of the fact that since we want to escape Earth's gravity, okay, that means that as we move away from Earth, right, FG is getting very small as R is getting very big, or so it gets very big. But as FG gets very, very small, right, in terms of its energy conservation, right, that means that the total energy is equivalent to its gravitational potential energy in reality. So we need to now we have to use the fact that what was I saying? Sorry about that. We have to figure out the gravitational potential energy somehow, okay? So the way to do that is to do this, okay? Is to take the limit, okay? So take the limit, right? So I'm going to write down here. Then we have, so also because of this, because of this, because of this, this, because of this. Because of this. And the potential energy is really going to be at its maximum. You have to think about that because we're talking about the potential energy at a very far distance, right? between two spherical objects, Earth and where the satellite is. Okay, so EG is increasing by a lot. Okay, so we have that. So for step 3 now we're moving into the execution phase. Okay, so the execution phase, okay, step 3 is the execution. Step 3 is the execution. Step 3 is the execution. All right, so step 3, we got this. What I mean by execution, we're going to do the limit. Take the limit as our satellite. Satellite approaches infinity of capital FG as a function of our satellite. Okay, our satellite. Okay, and this is equivalent to the limit as our satellite approaches infinity of G M Earth M satellite M satellite. Okay, satellite. Satellite squared. Okay, and we need to integrate both sides. I'm going to integrate from R to infinity on both sides. Now, how do I know to do this? Why do I have to integrate from R to infinity? Well, I want to go back to energy. Okay, so I integrate over the force, and this is all with respect to R, by the way. Yeah, be careful. Make sure you're with respect to R. If I didn't put the R, I made a mistake. Yeah, with respect to R. Okay, I need to integrate from R to infinity because so that's the mathematical part. The reason why I have to integrate from R to infinity is if you look back at our little planet here. Okay, let's look at planet Earth. Okay, the satellite, by common sense, will be on the surface of Earth, right? Okay, it's on the surface of Earth. There's our satellite. Can't be in the center. That won't make sense. So we're measuring from the edge of the surface of Earth. That's our Earth, right? So from the core of the Earth to the surface is the measurement our Earth. Okay, so we're starting from our Earth. Then this satellite, it rockets off from the surface of Earth, trying to escape Earth's gravity. So then we're going all the way out to infinity. I'm saying infinity because we don't know where in space it's going to land. It can keep going on forever. Okay, and the reason why it could keep going on forever is because of the inertia of the rocket. Okay, so let's do that. So that's how I know mathematically to integrate from R to infinity, or satellite to infinity. Okay. All right, so we're at step 3, and now we're calculating this. All right, so we know we have to deal with this guy here. So I'm taking the limit. So I take limit as our satellite. Our satellite is approaching infinity. Of GM Earth. GM Earth and satellite. Satellite. Integrate from R to infinity. Okay. dr over r squared. So this is what we have right now. So I moved the constants to the front of the integral, the GM Earth M satellite. Okay, these are constants. Next is, right, so I move these guys. This is all constant, GM M Earth M satellite. Next is now it's just a purely mathematical problem. So we need to figure out how to integrate with respect to r over r squared. So to do that, we're just going to take the limit as r goes to infinity of gm Earth, m satellite. Integrating this, we bring r squared to the top. So because it can go from r to infinity, r to -2. If I integrate this portion right here, okay, this portion right here, okay. Oh, thank you. Sorry about that. Some intruder came in. So yeah, we're back at it. So I'm integrating the problem here. So how would we integrate this? Well, the way to integrate it is using power rule. You should know this, right? So this is taking limit as r goes to infinity, gm Earth, m satellite. Integrate this part now becomes r -1, so r is -1 over -1. And we're having limits of integration from our satellite. By the way, put our satellite. I didn't put it down because I was lazy to put it down, so our satellite. By the way, a good mathematician is one that is lazy. Remember that. Well, it's not true, but I mean in terms of the acronyms, instead of doing every single step here. Okay, so we have the rocket all the way out in outer space, deep in outer space, right? So we should be getting, we should be deriving an expression for the gravitational potential energy at very far distances, okay? So if we get something like a GMM over R, we should be fine. Negative GMM over R, because the potential energy should be negative, given the fact that the energy becomes negative. It has to do with the fact. It has to do with the fact because of the binding energy. I'm not going to go into it. If you want to ask me questions on the binding energy, please put stuff below in the chat, or you can email me. It will be all in the link below of the YouTube video. Okay, so we're integrating from, yeah, it was our satellite. It was our satellite to R. Okay. By the way, I'm denoting R as it's approaching infinity. So I sort of made a boo-boo there. Put R there and the upper limit of integration. Okay. So now we got limits as our satellite. Our satellite approaches infinity. Okay. R -1 can be brought down. So this becomes negative G M Earth, mass of the satellite, over R satellite. Okay. And taking the limits of integration, R satellite, like to R, where R is approaching infinity. Okay. If you notice something a little bit weird with my notation, as I said, you can put the correction above. It's just a subscript problem. Okay, I made a subscript error. Okay. Now, with all this, as you can see, we have to put the limits of integration in. So doing that, we get limit our satellite approaches infinity, negative G M Earth M satellite going from the upper limit of integration, right? Because it's f of b minus f of a when you have a definite integral. Second, what was it? Fundamental theorem of calculus part 2. Okay, so we're going to take our satellite gets replaced with r, right? And then it's minus g m Earth m satellite over our satellites, close the parentheses, right? And we put square brackets here because otherwise we have problems. Okay, so now here it's just simple math here. Now we have limit our satellite approaches infinity. Make sure to if you need a break, pause the video. This is a long derivation. Okay. Even I'm getting annoyed by it, but it's long. Just bear with me here, okay? So we have minus gm, g times mass of Earth, mass of satellite, okay? Mass of satellite divided by r, and then minus and minus is plus. And then it'll be g mass of Earth, mass of satellite divided by r satellite, all square brackets. We're almost there. Okay. Okay, so now we have this expression here that's been simplified. All we have to do is evaluate the limit as our satellite approaches infinity, because the satellite is going to infinity. It's in deep space, right? So visualize that your satellite, right, was from the surface of Earth again. It rocketed out, right? Right. It's going to the atmosphere, okay? And it needs to keep pushing to reach a certain escape velocity. So that's why you get out of Earth's gravity and go into deep space until infinity. Okay. That's why those limits were bounded all the way from r to infinity. Okay, so now let's evaluate our satellite as it approaches infinity. Okay. So as our satellite goes to infinity, what happens as our satellite goes to infinity? If your denominator gets very large, what happens to the whole fraction? Well, the whole fraction is approaching a very small number, right? Think about it. You have a very large number approaching infinity without bound, and the entire fraction has to be going to zero, right? It approaches zero. So as r goes to infinity, the gravitational attraction of the satellite compared to Earth will go to zero, right? So as our satellite goes to infinity, then gravitational attraction goes to zero. Then Fg goes to zero. Okay, so that means that our satellite is zero. Not our satellite, but this whole thing is zero, right? This whole portion here is zero. Okay, so now I'm just left with this guy right here. Okay, so now I'm left with uh, minus g, gravitational constant g, capital M Earth, capital M satellite. Where are? Okay, so we got all this. Now that we have the gravitational potential energy equal to minus g mass of Earth, mass satellite divided by our satellite, Okay, so we got all this gravitational potential energy. Now, since the object is in very deep space, eventually it does come to some sort of rest. Even though it's still moving, it eventually comes to some sort of rest. Okay. Uh, so the gravitational potential energy will be equal to the kinetic energy, right? You understand? Because of the fact that in order for the object to launch in the first place, it was moving. The object to launch from the surface of Earth had to move at the velocity v. So since it moves at velocity v, it automatically has the kinetic energy. Okay, if it has a kinetic energy, that means it's equal to 1/2 mv squared. And that has to be equal to the gravitational potential energy to just before it stops in deep space. So we have, so then we can say, so then by conservation of energy, EK is equal to the gravitational potential energy at far distances. And this is purely by the conservation of energy. They have to be equal because it's conserved. The energy is conserved throughout the entire motion. Okay, so this is conserved by conserved. Energy is conserved. So the energy has to be conserved. It is conserved. Okay, so now we have this. So what we're going to put in is we're going to say 1/2 m satellite was moving. Satellite, okay, this is m satellite. By the way, this is all we're doing the execution step, by the way. Execution means we're putting all of our stuff in. Let me make sure I wrote that. Yeah, still a part of the execution, okay? Where we're actually putting our strategy from step 1 and step 2. Okay, so m satellite times v satellite squared, I'm going to say that's only my v here, is equal to g m satellite satellites m, we have m Earth divided by our satellite squared. Right, our satellite squared. Let me see that. Not our satellite squared, our satellite, because this is gravitational potential energy and far this is. Okay. Okay, so now we have all this. Notice how the mass of the satellite has to cancel. Yes, you can't argue against it because of the fact that the mass gets canceled out. In other words, the energy is independent of the mass of the satellite at very far distances compared to where it launched. Okay, so 1/2 v squared is equal to g m Earth over our satellite. Okay. So we want to solve for the escape velocity v, and here it is, right? We're going to get v squared is equal to twice, we multiply both sides by 2g times capital M Earth divided by our satellite. Our satellite, okay, that's what we got right now. Make the bigger. Okay. Hopefully you can see the screen. So much space, it'll be a studio. All right, so that's what we've got right now. If you're getting tired, please stick on board. We're very, very close to finishing. Have a cup of water or something. Okay. What you'll notice here is that v is equal to the square root. Just isolate both sides for v. root of 2 g m Earth over our satellites. And that's equal to the escape velocity. Okay. And we're done. We've done all three all three steps, right? Visualize, model, and execute. There is another one to verify. For homework, I want you guys to verify how can we get to verify that this result is correct, that the escape velocity is this. Okay. All right. So I use a systematic technique to solve this. You can try, as I said, to do the verification part of it. Okay. If you still have trouble with this type of concept, you can download my free guide. I have a guide on a PDF. It's on the systems technique that I use. Remember, the technique that you use is more important than just solving the problems. It's both a mixture of strong technique, system, and or understanding the definitions and formulas very well. Okay, that's what it is. A combination of those two things. All right. So you can download that. It's for free. And if you still have trouble using that technique, if you're having trouble with calculus-based physics, I also have, it's my book, first book actually. It's Advanced Integration Techniques. Okay, actually, I have it right here. I will showcase it. You can see in the camera. So it's this guy. Just one sec. All right, so this guy right here. If you're having trouble with calculus or calculus-based physics, now it's not going to help you. It's a terse book. It's a hard book, and I can't solve all the exercises. I made it probably a little bit too difficult. But what's really going to help you is the definitions and theorems that I put at the first part of it. Okay. So I structured it really well. I put definitions and theorems and some basic examples at the beginning to help with integration in case you were getting lost when I was doing the integral part of it, like the math-based part of it. This guy will be handy. Okay. It's going to help you develop your integration skills for those of you who need it. And it's also for those of you who want a major calculus-based physics challenge with open-ended problem. That's, I advise you though. And finally, if you don't require any resources, but you're really struggling and you need someone to guide you and through the intuition and problem solving, you can contact me for coaching. My link is below in the description. Okay, will be at the end of this YouTube video. Again, like and subscribe. For those of you who are new, please like and subscribe. It helps me and the algorithm and the channel. For those of you who already are subscribers, thank you again. I really appreciate it. I always appreciate if you can put chats below, something in the chat below. I like to communicate with the subscribers. All right. So I will start from next. I keep telling you guys, I'm promising next week 2 to 3 times YouTube. I think 2 is the golden number. 3 gets a bit excessive with everything else I have to do because I don't just advertise here and help people here. I do on other social media and then I have other things. So it gets a lot. So I'm going to do twice next week. I promise you. And problems will get more interesting, and we're going to tackle them together. Right. Once again, this is S.T.E.M Online Academy, helping you with hard midterm questions and exam problems that cannot be solved alone with AI. Thanks again, and have a great weekend.